You know, it's in the phone you're holding, the car you drive, even the building you're sitting in right now. There's this powerful, kind of invisible technology that's shaping almost everything around us. It's a tool that lets engineers literally see the future and then build it safely. Today, we're going to pull back the curtain on that tool, finite element analysis, or FEA for short. So, how does this unseen architect actually work?
Seriously, just think about that for a second. How do you know a bridge is going to stand up to a hurricane? Or that a brand new medical implant is going to last for decades inside someone's body? I mean, you can't just build a dozen skyscrapers and shake them till they break, right? The cost would be absolutely insane, and the risk, way too high. There has to be a better way.
And of course, there is. The answer is this secret architect behind so many of the things we rely on every day. It's how we get car frames that are light enough to save fuel, but also incredibly strong in a crash. It's how we build massive bridges that can take on insane amounts of stress. It's even how we design custom, life-saving implants for patients. It's called FEA, and it's nothing short of a revolution in how we design our world. Okay, so how does this incredibly powerful software actually work? Well, believe it or not, the core idea is shockingly simple. It's all about tackling an impossible problem by breaking it down into tiny, manageable pieces. And that's it. That is the big secret. Imagine trying to calculate every single force acting on something super complex, like a jet engine turbine blade, all at once. The math would be a complete nightmare. So FEA doesn't even try. Instead, it slices that one giant, impossible problem into thousands or sometimes even millions of tiny, simple problems that a computer can solve in a snap. Which brings us to the official definition. FEA is a computational method. It all happens inside a computer. It takes a digital model of an object and breaks it into a grid of these finite elements. By solving some pretty basic equations for each tiny little piece, and then adding all those solutions up, it can tell you exactly how the entire object is going to behave under real-world stress or heat or vibration. It's genius, really. The process itself is really logical when you look at it. First, an engineer creates a 3D digital blueprint of the object. Then comes the most critical step, meshing. This is where the computer dices up that complex shape into a grid of simple little shapes, like tiny pyramids or cubes. After that, they apply the simulated forces, like the weight of traffic on a bridge, and the software does the math for every single tiny piece. Finally, it stitches all those individual results together to create one big picture, showing the engineers exactly where the weak spots are. So by doing all this, what FEA is really creating is a digital twin of a physical object. This lets engineers test and tweak and perfect their designs in the virtual world before a single piece of real material is ever touched. And this idea? It's used almost everywhere. And the sheer breadth of its use is staggering. For civil engineers, it's modeling the crazy forces on a steel truss bridge. For mechanical engineers, it's absolutely essential for finding failure points in something like a high-speed gas turbine rotor. And in biomedical engineering, it gets really personal, right? Analyzing the stress on a custom-made dental implant to make sure it lasts a lifetime. It's the same core method, just applied to completely different worlds. But here's what's really cool. FEA isn't just about checking if something's going to break. It has become this amazing tool for pure innovation. Engineers can test brand new materials like advanced composites that don't even exist yet, all virtually. They can use a technique called topology optimization, which is basically telling the computer, hey, design the lightest possible car frame that's still super safe, and the software just does it. It's even used to perfect things like welding to make sure the manufacturing is flawless from the start. Now, as powerful as FEA is today, it's not standing still, not by a long shot. Thanks to huge leaps in computing power and artificial intelligence, the next generation of this stuff is going to be even more revolutionary. I mean, just look at the difference. It's night and day. What used to take hours or even days of number crunching is moving toward real-time analysis, all thanks to AI. Instead of guessing how a material might behave, neural networks can predict it instantly. And where engineers used to have to simulate just one thing at a time, like either stress or heat, they can now model multiple forces all interacting at once. And these future trends, they aren't science fiction. They're happening right now. AI and machine learning are being woven directly into the software. We've got new adaptive meshing, where the simulation is smart enough to focus its computing power on the most critical areas automatically. Multiphysics is becoming the standard, so you can see how things like airflow and structural stress affect each other at the same time.
And there are even brand new meshless methods coming out to get way better at modeling really tricky things, like how a crack spreads through a material. All right, so we've talked about a lot of advanced tech and complex code, and it might seem a bit abstract. But the impact all of this has on our daily lives is incredibly real. So let's connect all these dots back to the world we actually live in. Because ultimately, this is why it all matters. That skyscraper we talked about at the beginning, it can survive a virtual magnitude 8 earthquake before a single drop of concrete is poured. A new jet engine can run hotter and more efficiently because its designers could digitally predict metal fatigue down to the tiniest detail. It's all about building a better, safer, and more efficient world with confidence, one simulation at a time. You know, I think this quote just sums it up perfectly. FEA really is that bridge. It connects a brilliant idea in an engineer's imagination to its actual creation in the physical world. It gives us the confidence to innovate, to push the boundaries, and to build things that we once could only dream about. And that leaves us with one last, kind of wild thought. As these simulation tools get more and more powerful, getting closer and closer to a perfect digital copy of reality, the old limits of trial and error just melt away. And if that happens, the only true limit left is our own imagination. What do you think we'll build then?